Thank you all for having me. I am delighted to actually finally make it to Ashesi. I was supposed to come a year ago for the first time, but my flights ended up getting messed up and I wasn't able to make it. But I'm delighted to be here today. Thank you all for hosting me. I've sort of followed Ashesi from afar since I met Patrick in 2009, and it's great to see the campus and see so many exciting, fresh faces of excited students. All right. So today I'm going to talk about a bunch of exciting trends in machine learning. And this is presenting the work of many, many people at Google Research, Google DeepMind, and across the rest of Google. So first, a couple of observations. So in recent years, machine learning has really changed our expectations of what is possible with computers. I think if you look back even 10 years ago, computers couldn't really see, they couldn't really understand language all that well. They couldn't understand, speech recognition kind of worked, but not really. And we're now at a point where a lot of those capabilities have started to exist in computing systems. And that really changes what you think you might be able to do with computers to build all kinds of interesting applications in the world. One of the trends that has caused this is increasing scale. So larger amounts of computation, larger amounts of data applied to different kinds of learning problems, larger scale models as a result of that deliver better results. And this trend has been one of the things that's really pushed the progress in the last 10 years and looks to continue to push it in the next at least 5 to 10 years, I would expect. And the kinds of computations we want to run as a result of now doing much more machine learning are really different than the traditional kind of handwritten if then else kind of conditional laden C++ code or whatever. That's really a very different style of computation. And so that's really adapting and changing what kind of computing infrastructure, what kind of computing hardware we want to build in order to support these new machine learning based applications. Okay, so I said some of this already, but there's been a decade of amazing progress in what computers can do. And just highlighting a few of the different kinds of machine learned solutions that we can now sort of tackle or mostly tackle that we couldn't before. So the first is image classification, where you take in the pixels of an image, so the red, green, blue values in the image, and then you try to derive what is in that image as one of 1,000 or 10,000 or more categories. And so there you see an image, and the model can output leopard or garbage truck or bicycle or whatever it is. Audio waveforms going in and then emitting speech transcriptions. Speech recognition has existed for a long time, not necessarily using deep neural networks, but as deep neural networks have come on and been used for this approach, the error rates have dropped dramatically and made it much more usable. Translation, so going from text in one language to text in another. Again, translation quality has dramatically improved over the last decade. And we've even been able to see things that are sort of much more than just sort of explicit categories of what's in an image being output, and instead being able to have models that can output simple sentences describing what is in that image. There's a cheetah lying on top of a car. This is actually a vacation photo of mine, which was quite exciting. But perhaps more excitingly, and what you kind of hear about as generative AI, is actually being able to reverse some of these things. So that now, instead of the inputs being the inputs, they're now the outputs. So we can now take something like a category that we would like different images for, like leopard, and have a computer model that can generate plausible looking 100 different images of leopard-like things that don't really exist. They're not real photos. They're just sort of generated sets of pixels that have the right properties to be a leopard. Speech, text-to-speech has existed for a long time, but reversing that so that you take in text and produce audio waveforms is sort of a fundamental problem in producing realistic sounding speech. Translation is not that surprising to be able to reverse. But you can also reverse even simple descriptions of what you'd like in an image and generate plausible looking images for that. So I think these, the fact that you can kind of malleably change what inputs you want and what outputs you want into these sort of large scale machine learning systems and be able to generate images from text or be able to tell you what's in an image or what's in a video is really, really an exciting thing that has been sort of the dream of a lot of computing research in the field of AI for a long time, but it's only in the last decade that we've made substantial progress. So just to give you a sense of the progress, there's a contest called ImageNet, which is about categorizing the, starting with inputs as being color images, like the ones you see there, and then producing one of 1,000 different categories. And prior to neural networks being used in this contest, the sort of error rate, top 5 error rate was about 50.9%. And then Alex Ashesi, Ilya Sutskever, and Jeffrey Hinton introduced the approach of using a deep neural network for this contest for the first time in 2012. It was actually published in 2013. But they made a very big jump in accuracy by doing that. And they were the only team out of like about 30 that used a deep neural network that year. And that jump in accuracy was so startling to the computer vision community that the next year, 27 out of 28 teams used a deep neural network to tackle the ImageNet challenge. And there's been, actually, this leap was very large, but there's been a very large amount of progress and improvement in accuracy since then over the last, 8 or 9 years. So this actually benchmark is almost not that exciting because we're already approaching human level, we're actually exceeding human levels of error in this contest. It's actually pretty hard because there's like in the 1,000 categories, there's like 40 different kinds of dogs. So if a human tries to do this, they actually get quite a few errors. It's not like human error is 0. It's more like 12% if you don't train yourself for a while, and 6% if you train yourself for a while. And similar story in speech recognition. So this is actually a shorter time frame. So this is only 5 or 6 years rather than 10. But you see error rates on a particular speech recognition benchmark just going down dramatically from kind of usable to actually quite good and much more usable. We've also seen a lot of progress in language models, which I'll talk about in a little bit in the rest of the talk. But we've also seen success in taking general language models and then fine-tuning them, so giving them further training on sort of domain-restricted kind of material. And one of the things we've been excited about is the ability to do this on medical text. So you take a general language model and you train it further on medical text, and then you see what is the ability of this system to sort of pass the medical board exam questions. And passing is 60% there. We've done this now twice, once with a model called MedPalm, which got 67%, which we were excited to see it passing the medical boards, because that's reasonably good. And then 6 months later, we did it with a more powerful language model and fine-tuned it again on medical text and got 86.5%, which was like quite substantial progress in a 6-month period. So this is pretty exciting, and a lot of clinicians are excited about being able to sort of have a conversation with these language models about all kinds of medical topics. And then another trend is towards multimodal models. So rather than having just one modality as input, you put in an image, or you put in speech, or you put in text. Really, the ability to take in multiple of these kinds of inputs and produce interesting outputs is a trend that is happening, where you kind of glue together multiple pieces of a model and then often train it completely end-to-end on these multimodal tasks. So for example, this Pally system in the top takes in as input an image and then something you want to be done about the image, like generate the alt text, which is like a little description of this, and you can say generate it in Spanish or English or Hungarian. And then you can also, what type of flowers are in the bucket, and it says sunflowers. And then the bottom pictures are, the inputs are the description of what you want in the image. And then these are some of the generated images that these systems can actually produce. This is kind of nice for people without the ability to really create drawings on their own, like myself. You can actually ask the system to help you draw something you'd like. Okay, so there's a bunch of exciting trends. I think I'll talk about each of them in sequence in the talk. But more capable general models, major improvements in the efficiency of these models, and also in the hardware that is used, sort of ways in which this can be used sort of on device and really help people in sort of different situations. There's a lot of use of machine learning in engineering, science, and health and sustainability. So I think these applied areas of where machine learning is really starting to get traction of, supplanting some of the older approaches that were used in some of these fields or augmenting the approaches. And then being able to understand machine learning models at a deeper level so that we can sort of make sure that they are, doing what we want. Okay, so I'll talk about trend 1 and 2 in this section in concert. So one of the things we've observed is that these models get better and better the more computational power you're actually able to apply to the problem. And in particular, as data sets grow, you need larger scale models in order to sort of absorb the interesting information that is present in a data set. If you have a trillion words of text, it's not going to make sense to train a 100 parameter model. You want sort of a many billion parameter model in order to sort of understand the patterns that exist in that data set. And so the kinds of computations you want to do in machine learning models are actually quite different, as I was mentioning, to the kinds of computations you want to do in traditional handwritten software. And so machine learning optimized hardware can be much more efficient and also has been showing major improvements generation to generation as people sort of understand more about the kinds of computations we want to do. They build sort of more improvements in terms of getting onto more modern silicon fabrication processes and so on. And this enables larger scale models with both lower economic costs but also lower energy costs relative to previous generations. Okay, so the special computation properties that you can take advantage of when building machine learning hardware is really that reduced precision for neural network algorithms is actually totally fine. You don't need to carry out lots of computations to 5 or 6 or 7 levels, digits of precision. It actually turns out that a couple of digits of precision is totally fine. And why this matters is that if you want to build a multiplier circuit on a computer chip, building a multiplier circuit that only has 2 digits of precision actually takes up a lot less area on the chip. And so you can put in more multiplier units per unit area on the chip. And also takes a lot less power per multiplier. So that's kind of nice. And the other property that neural network computations have is that almost all of the machine learning algorithms, all the ones that I described in the first few slides of the different kinds of things that machine learning models can do, are really just different orderings of essentially what is dense linear algebra operations. And so that's a very restricted set of computational things, instructions, if you like, that you need to support. And so you can support all kinds of machine learning algorithms with essentially machines that are designed to accelerate and perform mostly dense matrix multiplies and vector operations at reduced precision. And so that means you can chuck out your idea of building a general purpose CPU and say, I'm going to build a reduced precision linear algebra machine, and that's all. And it's going to be great for machine learning. It won't be able to do other things, but it can really accelerate machine learning. And so that's one of the things we've been doing at Google for actually 8 years now, is really designing custom processors for machine learning. And there's 2 phases to machine learning. There's the training phase, and then there's the inference phase where you sort of already have a trained model and you just want to apply it. You want to put in an image and say what's in it, as opposed to train the model to do that process. So our first piece of hardware was really geared towards inference only. And one of the nice things about inference is it actually needs even less precision than training. So once you've already trained the model, you can use even lower precision. And so this system actually does integer-only, 8-bit integer-only matrix multiplies. And that's what enabled it to have about 30x advantage over modern CPUs and GPUs of the time at sort of performing machine learning computations. And then our second generation and our third and fourth are really focused on both training and inference. And so you can see, this system is 4 separate chips on a board. And those boards are actually designed to be wired up into larger scale systems that I'll show on the next slide. Version 3, we added water cooling to the chips so that we could actually run them at higher power and still keep them at a reasonable temperature. It's always very exciting when you have water running to the surface of your chip. So you need to be a little careful about leaks and so on. And then this is the 4th generation. And the second, third, and fourth generation are designed to be connected together into larger scale systems that we call pods. And so they basically, in this system, all those boards of 2x2 groups of chips actually end up being connected together into kind of a 16 by 16 grid of 256 chips, and have a 2D custom mesh network where each chip can communicate with its neighbors to the north, south, east, and west. And the third generation is just a scaled up version of that. The fourth generation actually has a 3-dimensional mesh. So it can communicate with the front and back as well as the other compass directions. And so, focusing on efficient machine learning hardware enables actually to be able to train larger scale models that are sort of more effective at a lot of the tasks that I described. And so one of the things that has happened is that a lot of advances really have depended on being able to understand text better. There's a lot of problems in the world like translation or summarization or question answering that if you can really have a better model that can predict the kinds of textual outputs you'd like given the textual inputs, that actually is really can enable you to do a lot of different things. So there's been a lot of improvements in this. And a lot of those improvements are really driven by a sort of new style of machine learning neural network architecture called the transformer model that was developed by a bunch of Google researchers plus an intern in 2017. And this is the sort of relatively famous now attention is all you need paper, which introduced this concept of a transformer which can look at a whole bunch of different pieces of input in parallel. And this is in contrast to a recurrent model, which sort of had a very sequential process of looking at a whole sequence of things. So this is number 4 on Nature's 2020 list of most influential scientific papers published between 2015 and 2020. Has 85,000 citations, which is quite a large number. One interesting thing about that list and the sense in which machine learning is sweeping not just computer science, but all sciences. Like Nature is primarily a all general science kind of journal. The first non-machine learning paper on this list was number 5. So regardless of if you want to study computer science or whatever, or you want to go into more general sciences, machine learning is going to be an essence and core of any of these fields. Okay, but the big improvement that the system was able to make compared to the recurrent models that were popular at the time was really that it could process a bunch of text in parallel. You process 1,000 words with one computational step rather than what the recurrent models at the time, which have some state, and so they look at a word, they do some computation to update that internal state, and then they go on to the next word, and then they do some computation to update that. And so that sequential process really meant that they were quite slow at being able to process very large amounts of text or to be able to train on large amounts of text. And so the transformer model just said, we're going to look at all the text at once and then have an attention mechanism where, predicting this word, we can look backwards at the whole state that we've computed over and be able to sort of use pieces of the input text or representations of it in order to figure out how to generate the most plausible output. And so you actually end up getting higher accuracy, but with way less compute, like 10x to 100x less computational cost versus the recurrent approaches. And that, combined with the improvements you get in efficiency by using machine learning-oriented hardware, really mean that all of a sudden you're getting 10,000 times improvement or something, 100x from the hardware plus 100x from the better algorithm, over what you could do before sort of these innovations. And that all of a sudden means, much larger models that are much more capable become possible. And so just to give you a sense of how powerful these models are, one thing I would say is these models are actually trained on a really simple objective. So they're trained in an unsupervised manner, which means, or self-supervised, where you basically take a bunch of text, and the objective you give to the model is, given the past, few hundred tokens, a few thousand tokens in some cases, can I predict what is the next token? And the nice thing about using real text is you actually have the right answer, right? You have what that text was. I really like to play the, and then the model tries to guess what word is there, and maybe the real text says xylophone, and if it gets it right, great. If it gets it wrong, then you give it a little bit of feedback that, hey, you really should have said xylophone, and next time you should try your best to say xylophone in this context. And that's really all the training process is doing in these models, is predicting the next token. It's kind of startling what these models are able to do from that simple objective. Okay, but let's look at what they can actually do. So we've been developing these models internally for quite a while. We've actually released a product that is more of a conversational product called Bard, where you can just have a conversation with it. You can ask it pretty much about anything, and it will kind of come up with some plausible sort of response. So here I said, can you reverse the letters of hot chips and tensor processing unit for me? This is actually from a talk I gave last week at the Hot Chips conference, which is why I'm asking it to do that. It says, sure, the reverse strings of hot chips and tensor processing unit are, I won't try to pronounce it, but it got it right, which is good. But it then goes on to say, okay, so this is already sort of like cool. I actually gave it sort of a fairly high-level English direction of what I would like it to do, and it was able to do it. But then it goes on to say, I can also do this for you in Python. Here's the code. Reverse string, blah, 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 print reverse string of that. And then it says, there's the Python code. Maybe I could explain it for you. The code first defines this function, takes a string as input, returns a reverse string. It works by looping through the string from the end to the beginning and adding a letter. That's kind of helpful. If you're not familiar with programming, and this is kind of your first experience with programming, it's kind of nice that it is able to sort of generate simple programs for you, describe how they work, in response to a relatively innocuous English prompt saying, hey computer, can you do something for me? And then it helpfully says, is there anything else I can help you with? So I think that's pretty amazing. As a computer scientist, I find that pretty cool. And I hope you do too. You can also then continue the conversation, tell me more about TPUs. That's the special purpose hardware I just described to you. And it says, sure, TPUs are special hardware designed to excite. It could almost give my talk, actually. TPUs are specialized hardware processors. They can help improve the performance and efficiency. This text doesn't exist in this form on the web. There's little snippets of this or that on the web in the training data of the model, and it's able to sort of synthesize this response from the data it's been exposed to. So we've also been working on system software on top of the underlying hardware to make it easier to express interesting machine learning computations. So one of the systems that we've been working on is a system called Pathways, which enables us to actually flexibly map machine learning computations onto those sets of actual physical chips. And we actually can also gang together multiple of those pods together to form larger scale computational units. So you can map sort of half of your model onto the pod on the left, half on the right, and then the underlying system can take care of deciding, okay, if I need to communicate from here to here, that's actually on the same pod, so I should use the efficient network that exists within a pod, and if I have to talk to a chip on the other side, then I will use the data center network to sort of use that, and the data center network is slower and has less bandwidth, but it's kind of nice that as the developer of a machine learning model, you can mostly ignore that, and the system will sort of take care of trying to do the most efficient thing it can. Okay, One of the things that has also been nice is that encouraging models to show their work actually can improve the accuracy and interpretability. So I'll give you an example here. This is a technique called chain of thought prompting. So in standard prompting for a language model, sometimes you give it an example of the kind of problem you'd like to solve, and then you give it the real problem that you'd like to solve. So here it says, here's the example problem. Sean has 5 toys for Christmas. He got 2 toys. How many toys does he have now? Answer's 9. And then the real question without the answer, and then the model is supposed to spit out the answer for the second question. And you know, language models are not perfect. They hallucinate, they make stuff up. They're like, oh, I think the answer is 50. Completely wrong in this case, but hey, it's okay, it produced some text. But one of the things that, if you recall back to your 5th grade math teacher, they really encourage you to show your work. And part of the reason is that that can help, you know, the teacher in that case understand the sets of steps you're going through in order to solve the problem. And it turns out the same approach works for language models. You can say, you know, you really should show your work. So I'm going to give you an example where the work is actually shown for the problem. And then I'm going to ask the other problem and say the model will then sort of be prompted to and sort of conditioned to then actually show its work for the second problem. And so then, in this case, the model works out how to do this problem and actually gets the correct answer. And even if it didn't get the correct answer, one of the nice things is you can really see where it went wrong. Sort of the same way your 5th grade teacher could tell from your homework, you know, did it go wrong or right, and where. So that's kind of exciting. And it actually makes a huge difference in accuracy for different kinds of benchmarks. So these are sort of arithmetic reasoning or 8th grade math level problems. And you see that the model, as the scale goes up, the general blue model without chain of thought prompting sort of improves a little bit, but not substantially. But when you start to add chain of thought prompting and you get to a certain size model, then the model is actually able to do this multi-step reasoning in a much better way when it's sort of encouraged to do so. So that's a sort of, one of the nice things about this technique is you don't need to change the way you trained the model. It's really something you can just do at inference time. You just say, hey, can you please show your work? And here's an example of showing your work. And then off you go. Okay, so what about harder math and science? Well, same kind of approach works. You can actually, in the same way that I mentioned fine-tuning on medical text, you can actually fine-tune on more mathematical text and things with proofs in it and sort of mathematical, you know, research papers and so on. And then once you do that, then you can ask the model to train, to produce answers to more difficult mathematical questions. You know, assume that the variance of the first n numbers is 10 and the variance of the first m is 16, even natural compute m plus n, or, you know, for every a and b not equal to a, prove something. And so if you fine tune one of these language models on scientific paper content, which is LaTeX input for archive, you can actually get pretty good results. And so here's a couple of examples of the questions on the previous slide with the model output. And in this case, it's correct. It's not always correct, but you know, it's pretty complicated. And it's actually able to produce, you know, a reasonable proof on the right-hand side for that proof one, and sort of figure out the answer for m and n on the left-hand side. And so this generated a huge improvement in a few different benchmarks, and particularly in the math benchmark. The published state of the art was 6.9%, and then the system went to 50%. And the other improvements were, you know, more modest, but pretty substantial improvements in state of the art on a bunch of mathematical reasoning kinds of benchmarks. Okay, let me talk now about sparsity. I think, you know, if you think of most machine learning models, most neural network models today, they're dense, which means they have a bunch of layers, each with a bunch of neurons, and every layer is fully activated. So we feed in the input to the first layer, all the neurons in there look at the input, decide what they're going to do, produce output, and then we activate all the neurons in the second layer. And so essentially the entire model, if it's a 10 billion parameter model, 10 billion parameters are activated and used in multiply operations in order to produce the output of the model. But that doesn't necessarily make the most sense, right? Like we might want only part of the model to be activated for a given example, because we know in real brains there's different parts of your brain that are good at different things, right? When you're reading Shakespeare, the part of your brain that's like really about very fast vision tasks so you can like avoid falling down probably isn't as active as when you're walking. And so you might want machine learning models to be able to have different pieces and to call upon those different pieces at the right times. And so one of the things we've been exploring for a while is how can you build these kinds of sparse models where you activate only pieces of the model. And one of the things we've developed is a technique called sparsely gated mixture of experts. So the pink part here is a traditional dense neural network layer. And then what we're going to do is introduce a bunch of experts in between the two pink layers. And these experts are going to be additional capacity in the model. It might have a few million parameters that get learned. And you have a bunch of experts, in this case 2,048 different experts. And importantly, that green bit there is going to learn, as part of the overall learning process for the model, which experts are good at which kinds of things. So you can think of the gating network as predicting which of the 2,000 experts this example should go to, because I think this expert is better at this kind of thing. And then it can actually get an error signal back as part of the learning process into the gating network as well. One of the things it can do is send it to two experts and see which expert sort of had less of an error on the example than the other. And if that was not one of the experts it predicted most highly to send it to, it can actually make adjustments to the sort of learned gating network, so that next time it'll be a little bit more likely to send it to that expert because it seemed better at this kind of thing. And so this is all can happen in the same unified learning process. And what actually emerges in like a language model developed this way with different kinds of text is the experts develop, the ability to be good at different kinds of things. So this expert might be good when you're talking about biological terms, or this expert might be really good at dates and times. This one might be good at kind of adverbs that are about running fast. And the advantage here is you actually get substantial training speedups where, in the time to reach a given accuracy, the dense model here in the red is actually much slower than the a few different models, sparse models. This is all trained on the same amount of computation. So you actually get a 7x speed up. This is, again, one of these things where you get major algorithmic improvements that give you, factors of 7, factors of 10, similar to the original transformer paper, that really are multiplicative on top of any hardware advances. And this enables you to train very large models that are sparsely activated. And so this is an example of a larger model that was trained on a many language translation task, 100 different languages. And the baseline here is a separate translation model for each language to English. And what you see is that the languages are ordered on the x-axis according to how much data we have about each language. So the languages like French or Spanish, where there's a lot of English to French or English to Spanish data, are on the left, and lower resource languages where there's not very much data about, say, English to Twi or English to Swahili are going to be towards the right. And so the y-axis is blue score, the change in blue score compared to that baseline. And blue score is a measure of translation quality, so generally higher is better. And what you see is that if you train a dense model on all the languages together, That's the dotted line there. One really nice property of both the dense and the sparse models is as you're training a unified model across all the languages, you see improvements across all the languages. You see some improvement even in the languages where you already had a lot of data for, say, just English to Spanish. So you could have trained just an English-Spanish model, but training a unified model across all 100 languages actually improves the English to Spanish quality somewhat, even though you already had a fair amount of data for that case. But where you see the most dramatic improvements for all the models is where you have low resource languages, where you don't have much data for any individual language, but now all of a sudden by training across 100 languages, the system is able to do transfer learning and get better sort of language quality, translation quality, especially for the languages without much data. And then what you see is the improvement of the sparse models versus the dense model on the right-hand side is quite substantial. So if you look at the green line versus the dotted line, that's a substantial improvement in translation quality for all the language pairs really, but especially at the right-hand side. Okay, so we actually do want to train these kinds of sparse models, and we need to be able to map them onto computational devices in some way. Currently, the system I showed you had experts that were all the same size, all the same computational cost. So all the green boxes were the same size. We're not quite doing this yet, but one of the things we'd like to be able to explore is where the experts themselves have different computational costs. So maybe you can have a very cheap expert on the left-hand side there that is, maybe used for 90% of the examples because most things are easier. And then occasionally when something is very hard, you invoke a much more computationally expensive expert, but you do that only rarely. And then you need to be able to map that onto hardware somehow. So you might map the right-hand side onto 16 chips and the smaller experts on the left-hand side onto just 1 or 2 chips. And that's what the pathway system I mentioned kind of enables us to explore, although we haven't really done so yet. Okay, generative models of images. This is an exciting and developing field. So the goal of this work is really to transform how the creative process works. So if you're thinking about something and you're like, oh, I just wish I had this image for my class presentation, and if it had a beautiful starry night with swirling things and some mountains, maybe you can make up that. So an MIT faculty member says, image synthesis is the biggest innovation in image making since the invention of photography 200 years ago. So that's a pretty bold statement, but probably not incorrect. It's the ability to really have computers help us take the things we have in our head and create images from them is going to be amazing. We have 2 different models, Party and Imagine. They actually have somewhat different algorithmic approaches, and I'll show you some examples from each of them, and then I'll walk you through some of the differences. But the fundamental idea is both algorithms work pretty well and can generate pretty cool images. So help humans reach their full. Okay, so this is the prompt on the left, oil painting generated by artificial intelligence, and the model comes up with that. Kind of cool. Steam train passes through a grand library, oil painting in the style of Rembrandt. So in the training data, the model has seen a bunch of Rembrandt images as well as all trains and things like that, and so it's able to synthesize these ideas. It's a little dark in the room. It actually shows up better on my screen, but wet dry. I don't know what I would come up with for wet dry, but that's as plausible as anything. A giant cobra snake made from X, and you can fill in different X's, so corn or pancakes or sushi or salad. So these are kind of fun, right? Like these images don't exist in the world, but you can sort of unlock your creativity and have your favorite giant cobra salad snake. A photo of a living room and a white couch and a fireplace, an abstract painting is on the wall, and bright light comes through the windows. Sure, I believe it. Much more complicated ones. A high contrast photo of a panda riding a horse, wearing a wizard hat and reading a book. Horses standing on a street against a gray concrete wall. colorful flowers, and the word peace is painted, so it kind of got peace, maybe not quite. DSLR photograph, daytime lighting. And there you go. Small, beautiful organic sculpture made of concrete. Sure, I guess. This is one where we had an external artist come in and play with these models as we were developing them. And I think she sort of went off on a weird fruit and vegetable kind of mode, creating all kinds of weird images. So I didn't show the prompts, but you can imagine what they were. Photo of a frog reading the newspaper named Today on it. Frog printed on the newspaper too. Okay, I think in the interest of time, I'm going to mostly skip how these models work. But the basic idea behind Imagine is you have a language model hooked up to a computer vision model that generates a first sketch at a very small resolution photo, 64 by 64 pixels. And then you have a cascade of models that work in conjunction with the language model representation plus the smaller image to then fill in more detail in the medium scale image, and then do that one more time to fill in the detail on the larger scale image. So this is like a golden retriever dog wearing a blue checkered beret and red dotted turtleneck. And then it kind of fills in progressively more detail. The other one is a model that is trained in a slightly different way. I'm not going to go into the details, but essentially it takes in images and text and then uses the actual image from the text training data set. So you have training data that is text, sentences plus images, and then the model tries to generate an image given just the text, and then it gets an error signal based on how far away from the real image it is in terms of generation. Model scaling really brings improvements to these. So these are the number of parameters in the model. So you can think of this as roughly proportional to the amount of compute used to generate the images. So a 350 million parameter model, it's the same prompt for all four of these models. A portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends." You know, the 350 million parameter model doesn't really get that right. It's got some plausible attributes about that, but it's not really correct. And then you can see as you increase the scale of the model, it now, at 750 million, starts to know what the Sydney Opera House is. The sign is still completely garbled. 3 billion parameter, the Opera House is looking pretty good. The sign is still, looks more like letters, but it's still meaningless relative to what we asked it to say. And then the 20 billion parameter model actually gets, you know, the Opera House right, gets the sign text right, which is a really hard thing to do, is actually have these models render text in there that was in the prompt in the right way. And also is, you know, high resolution and looks good. So this is just essentially that same message in sort of more detailed analytic form, but it basically says as you scale the models are more adherent and better quality to an objective that we measure. Okay, so where are we headed? So we've already kind of done a lot of this move of separate models for different tasks, which was kind of what we did, you know, the first 6 or 7 years of the deep learning revolution that started in 2010 or 11 or 12, into single models that can actually generalize across millions of tasks. So that language model I showed you, you can ask it to do a bunch of different things, and the system will, you know, at least give it an attempt. And you don't necessarily these days train separate models to classify leopards versus classify, you know, some other image classification task. You try to train a general language image model that does many things. Dense models, which I described, are, I think, going to give more and more way to efficient sparse models, where you have a very large model, but then you call on the right, you know, 1% of it or 10% of it rather than activating the whole model for every example or every token or every situation. Single modality models, where you just have images as input or just have speech or just text, are already giving way to models that deal with many different modalities, both on the input side and the output side. You can put in any combination of images and text and speech, and then ask it to generate me some speech that is appropriate for this image and text, or put in this video and describe it in text, or the model will be able to deal with all those different kinds of combinations. Okay, I'm going to go quickly through these parts, which is talking about some of the ways in which you may not realize, but there's actually a lot of machine learning running in interesting ways on phones. So one of the things that you may have observed is that as you've gotten newer phones, the camera quality on those phones has gotten quite a bit better. And a lot of that is due to better sensors, but an awful lot of it is due to interesting on-device computation that really improves the raw quality of the data coming off the sensors in order to improve the actual final quality using machine learning and other computational photography techniques. This enables, for example, things like cameras that work in very, very low light conditions, so it can take in actually a whole bunch of raw captures of the sensor and then sort of integrate them with image processing to be able to extract the most amount of light out of those images, even if your camera is shaking a little bit because you're holding it in your hand or whatever. It can sort of correct for that and give you, really high quality images that almost look like they're taken in daylight, even though it's very low light. Astrophotography is kind of an extreme example of that. Portrait mode enables you to kind of blur the background as a true professional photographer would and keep the subject in the foreground in perfect focus. That's something you can now do without photography skills, which is nice. We've also been exploring post-processing of images so that you can, if you took this really nice photo on the left and you say, oh, those telephone poles, if only they weren't there, and you can just kind of rub them out. And machine learning will sort of in-paint what it thinks should be there based on the properties of the image and trained model. Same thing with the people on the right. Oh, if only those people weren't in my nice waterfall photo. Oh, well, there they go. And then there's actually a whole bunch of things you can do on the phone by a better understanding of spoken language, text that you see on the screen, text, spoken language that other people might be saying into a phone call, for example. And so we actually have a whole bunch of things that actually provide a lot of value for people using their phone in various ways. So we can, for example, I use this all the time. If someone calls my phone and I don't recognize the number, you can screen the call. And so there's an automated machine learning system that will sort of say, oh, hello, I'm an automated system for Jeff's phone. Could you say a little bit about why you're calling? And then they will use speech recognition to transcribe whatever it is they say into something that just shows up on my screen. And then I can say, okay, yeah, I do want to talk to you because it's about the plumber who's supposed to come at 4 p.m. tomorrow. Or it's spam and I don't want to deal with it. Live caption enables you to watch any video on your screen, and then the video that's playing, we can do speech to text on the audio track of the video, and then we can sort of superimpose subtitles on the video that's playing for any video, like anything on the phone. So if you're watching a video and you don't want to turn the sound up on your phone, or it's not appropriate, or you're hard of hearing, you can actually get live captions on any material. You can read out text out loud from taking the text and then doing text to, speech generation. So this is all kind of examples of product features around flexible being able to deal with any modality or turn one modality into other modalities in different ways. And so I think this is a nice example. There's going to be a lot more of this stuff in the future. It will probably meld into something that is less many distinct features and something that is more sort of integral to, you just expect your phone to be able to deal with all these kinds of modalities and do the right thing. A nice example of this is This is read aloud and lens working together, so it can do optical character recognition on something in the image viewfinder or in the camera, and then can speak it out loud. And so, for example, for people who maybe don't read a particular language very well, it can actually tell you, what is in this box of stuff that I'm working to make something with in my kitchen. Okay. Growing impact in engineering, science, health, and sustainability. One of the things, so we have a research lab in Accra, actually, and one of the projects that's sort of the most mature in that lab is in using satellite imagery to improve our understanding of buildings in the world. And in particular, an accurate sort of understanding of building footprints is really important. It improves the quality of maps. So like knowing where buildings are is pretty important. It can help with population estimation, urban planning. In some situations, it can help with humanitarian response and environmental science, so you can study trends over time. And it's actually pretty hard. So these 4 examples don't actually have buildings, or at least things we don't want to count as buildings. These are pools, these are rocks of various kinds. This is a enclosure wall, but I wouldn't classify it as a building. And then this is different shipping containers. So, but from satellite imagery and from some labeled data of which things are buildings and which things are not, we can actually create a machine learning model that can identify building outlines and then use that data to improve maps. And the team here focused initially on African countries, and so we were able to identify, I think, something like 500 million, 600 million buildings in Africa. And then we've since expanded that work to run it on other satellite imagery and cover Southeast Asia, Indonesia, other countries there, as well as parts of Latin America and South America. And so what you see is it takes in a raw satellite image, and then it does some semantic segmentation of the pixels of that image, trying to identify things that look like they're connected together as part of the same building structure, and then identify things that are then different buildings as opposed to part of the same building. And then from that, you can actually create much higher quality maps and more detailed maps because you now know all the buildings, and that gives you a better sense as a user of Google Maps. I'm going to skip that. Yeah, 516 million distinct buildings. And so there's a nice research paper you can go read about.
So we're now at 1.8 billion.
Yeah, we're at 1.8 billion buildings now across all the different continents we've run it on, which is pretty cool. It's a lot of buildings. It's like a quarter of a building per person. Another area we've been doing a lot of work in is weather forecasting. And traditional forecasting methods really use these very computationally intensive physics-based models of the atmosphere and the current conditions, and then try to run them forward to understand how weather is going to develop in the next 3 hours, 6 hours, 2 days, 5 days, or whatever. And the typical way you do this is because these models have some uncertainty about things, you actually take the current conditions and then you start off 20 separate runs of these with like slightly perturbed versions of the current state. And then you run this ensemble of 20 different things, which are each quite computationally expensive, and you run them forward for a while, and then you kind of look at them all together and you average them together in some sense and give you a forecast for what's going to happen 3 days from now. And this takes a lot of computational power. Like some of the biggest supercomputers in the world are used for weather forecasting. And one thing is, could machine learning enable us to learn the physics underlying weather instead of hand coding it and doing very detailed numeric calculations to do weather forecasting? So we'd like to be able to go from an observation of the weather to a forecast. And one of the really nice properties that weather forecasting has is you have a lot of historical data. Like a year ago, there was some current state of the world, and then you have the state of the world the day later. And so you can use the year ago state to then try to predict the state 1 day later, And that gives you, a whole bunch of training data for these models, because now all of a sudden you can observe all the past, historical weather, and then use that to then predict future weather. And since weather is often about, what are the current patterns of, pressure and atmospheric conditions, this enables you to then generalize from the past to the future. And so this is a system that actually runs on a TPU, and one of the nice properties it also has is that typically the numeric simulations take hours to run to generate a 12-hour in advance forecast. And instead, we can now take just the raw observational data and produce as output a forecast in order seconds. And this is actually a trend you'll see in lots and lots of sciences. There's some computationally expensive process that is typically used in that science for numeric simulation or whatever. And you can often find ways to replace that with a neural network-based learned approximation of that much more expensive computational process. And then that enables you to then do science more quickly. We've seen this with chemistry simulations, for example, where there's a very expensive chemical molecule simulator, and you can replace it with a neural network that is 300,000 times faster. And that enables you to do completely different kinds of things than you could imagine doing if you had something that was not that fast. As I said, Earth provides the input and the output. And so this actually is working quite well, which is good. Okay, and then I'm going to briefly mention, learning from medical imaging. So this is a really, specialized kind of image classification and image detection problem for various kinds of healthcare problems. There's a whole bunch of different sort of modalities and sub-problems in this in different fields in, for example, ophthalmology, using images to detect diabetic retinopathy, which is a degenerative eye disease, which is something everyone should be screened for if they're at risk for this, and everyone who has diabetes is at risk for this. And so really they should be screened every year, but there aren't enough people in the ophthalmologists in the world with the training to screen people. And so actually if you catch this in time, it's a very treatable disease, but if you don't, you can actually go partially blind or fully blind if it's not caught in time. So the screening is super important, and this is where a machine learning-based model can actually help quite a lot. And then some imaging problems are much more about 3D volumes. So, things where you have like an MRI thing, you get a three-dimensional set of points, and you need to be able to detect things. So I'm not going to talk about all these in detail, but in general, I think the machine learning improvements in accuracy for these models has really dramatically affected what we now can do in the medical space. And there's a huge amount of exciting things in machine learning and AI for healthcare, both on the kind of textual side as well as on the kind of medical imaging side. And so our diabetic retinopathy work, which is probably the most mature of the ones I showed on the previous page, is actually being used to detect diabetic retinopathy in India and Thailand and France and Germany. DermAssist is something, dermatology is an interesting medical imaging application because unlike most of the other ones where you need a special eye camera or a special, radiology machine in order to actually collect the image, a lot of dermatology problems, just a camera on your phone, is sufficient to collect the raw data. You might need to make an assessment of, is this something I should really be worried about or not? And so every consumer kind of has a dermatology capable device in their hands if you can create a useful model from it. And so DermAssist is a technique where now you can just point your phone at something on your arm or whatever, and you say, is this like something I should worry about? Or is this a rash? Is this poison ivy or whatever? And it can actually do a pretty good job of this. Okay, and then I want to close with deeper and broader understanding of machine learning. I think one of the things that we've been thinking about at Google is how do we want to approach machine learning for tackling different problems in our products and in research that we do. And we, in 2018, more and more people across the company were using machine learning in various ways or thinking about using machine learning. And we wanted to have a set of principles by which everyone in the company should be thinking about applying machine learning or not. And so we came up with a set of 7 principles. Be socially beneficial, avoid creating or reinforcing unfair bias. One of the things about machine learning models is they train on data, and if that data itself is biased in various ways, then the machine learning model that you train will learn to replicate those biases and perhaps even accelerate them, because now you can have a much more computationally focused approach at making similar decisions. And so you might actually accelerate things by having something that is an automated model that replicates human biases. But there are ways of making sure that your model is not biased, or not biased in certain ways that you don't want. Testing models for safety, privacy is a super important thing in some domains of machine learning, and so on. So one of the things I want to point out is that a lot of these areas actually are very active areas of research in the machine learning research community. And so the approach we're using is we want to use the best known techniques that we know about in the community today for example, eliminating bias in our models, unfair bias, but also continue to work on research that advances the techniques to do a better job of understanding and eliminating certain kinds of bias or making models safer in various settings. So here's one example of gender bias in translation is a very common kind of bias that exists because often the text you train on, for example, has a lot of representations of my doctor is a friend of mine, he said, or whatever. And so the model associates doctor with the male gender because there's more text in the world that talks about male doctors than female doctors. And so my friend is a doctor in a language without gender, getting translated into a language with gendered pronouns, gendered nouns. The model, if you leave it on its own, will learn the bias that exists in the world, in the text that it's been trained on. Mi amigo es doctor is the male version of friend in Spanish. And so one of the things you can do is you can actually generate training data algorithmically to generate alternative gendered versions of training data, and then use that to sort of inform the model and then actually make it so that it behaves in a better way. In a lot of cases, you don't actually know the gender of if you're going from a language without a gender to one where you have to sort of pick a gender in order to produce a grammatical sentence. So one of the things we've chosen to do in our interface is actually show both alternatives and that enable the user to say, oh yeah, there is a choice here and I have to figure out from my own context what makes the most sense. So mi amiga es doctora or mi amigo es doctor. And this approach has really been able to eliminate a lot of bias in the translations for different languages pairs, especially ones where you're going from gendered to non-gendered to gendered languages. And then being able to understand the predictions of these models, often visualizations can really help. So this is a language interpretability toolkit that one of our research teams developed to really help us understand these large transformer language models and what is going on inside them. Why are they making this kind of prediction for how to complete a sentence as opposed to this other kind of completion? Really allows people to kind of interactively explore what's going on in these models. And I'm not going to go too much into depth. There's these 5 exciting trends. I think they're pretty exciting. I hope you're also excited. And machine learning, I think, is really making major progress on solving problems that we didn't sort of know how to solve in other ways. And that's really enabling computers to perceive the world around them in ways that they couldn't before. If you think back 10 years ago, computers couldn't really see. Now they can see. And that has pretty profound ramifications for what we can imagine computers doing, what we want them to do in the world, and so on. I'll leave this up, but thank you all for listening. We have a couple of different programs that might be of interest to you all. For those of you thinking about going on to study for PhDs, after you graduate. There we have a Africa PhD fellowship program, which provides mentorship as well as financial support. But you get assigned a Google Research mentor to kind of help you throughout your PhD career. And we also have conference scholarships for those who want to attend conferences and have accepted papers at different computer science conferences. So with that, thank you all very much. Thank you for your attention.